I'm Giorgio Metta. I'm from the Italian Institute of Technology, a research institute based in Genoa, Italy, and I work on human robotics, and in particular I'm the coordinator of the ICAB project. Today I'm going to speak about the ICAB, Human Robotics Project developed the Italian Institute of Technology. So the next video shows, let's say, the combination of these two things, the fact that a robot has learned the size of a tool and uses the tool to actually push a toy car. This is an example that, it's kind of trivial again, but it combines small modules that have machine learning in each of them together to make a more complicated behavior. So in the video, it goes on and on showing the robot pushing and observing the behavior of the object. So it can also take all this information to refine its internal models about the behavior of the different objects. And this is also a first step in another topic, which is understanding the physics of objects, because most objects, to be manipulated, you actually need to understand how heavy they are, how they behave under various stimulations. So this case was just pushing, but it can be more complicated exploration. The problem is that it just takes longer if you have more complex, let's say, exploration you like to perform. So the example we like to basically show is the use of a tool that is useful for bringing something closer to the robot so that the robot can actually grasp it. The sequence here, it's a 4 snapshot from an experiment where the robot uses the rake, brings the object closer, and then replaces the rake and grasps the object. So these are all elements of a common experiment. The one thing that is, let's say, a bit more complicated about all this idea is that you have to identify the tool and to map the view of the tool into the actual actions you can perform. So what we've done, and this mapping between vision and action is sometimes called affordances. There's a whole bunch of, let's say, robotics experiments in this direction. So I just wanted to introduce the word so that it's understandable later on. So what have we done? So we've taken a number of possible tools. There are 4 shown here, but it can be more. And also we ran experiments in simulation to cross-check. These tools are viewed by the robot, so the robot can understand the size of the tool, but now it can also change the orientation of the tool. This is important because a tool is not working well only because a certain size, but also because you change the use with respect to the object. So wanted to test for different orientations and make this into the learning procedure. So visually, we wanted to be able to sort of understand the orientation of the tool. We had no idea how to do that. So what we done was to take a huge number of visual features, take all of them, all visual features that may be related to the shape of the object that you're observing, and let the machine learning select the best features for the actual recognition of the tool. Here, the point is that we want to do a bit more than just recognizing a given tool in the hand of the robot, which is recognizing the orientation and the configuration in space, which is, unless you have 3D information, it's an open question how to do it. So this is basically the visual pipeline. It shows various snapshots. There's an image from the robot. There's an initial segmentation. And this happens because we can actually see the segmentation to the tool tip because we know where it is. We shown earlier how we can actually learn the size of the tool. And then there's a bit of image processing to actually select this region, and then we extract features. The extracted features, as I said, are a vector of 120 numbers representing all possible information about edges, about the shape of the object, and so forth. And the method that we use is shown here. What we have is this random action generation by the robot. So the robot tries to pull the object closer, reaching at a given point with respect to the object. So either to the side or central or to the left or to the right and so forth, and tries pulling and then observes the results. So if the object is effectively closer once the robot is finished, then it means that that was a good result. If the object doesn't move, it means that that was a mistake. So then what we done was, again, to use a kernel method, not surprisingly, to do the machine learning out of this. So to map the visual features to the best possible action. So that's basically what we want to achieve. Since the data was fairly complicated, we also have a clustering procedure in between. So we wanted to cluster similar set of features into a single class, because then it's easier for the machine learning to actually recognize the situation. And then we do this mapping from this training data that the robot can acquire autonomously. And when it's time to use a tool for a new action, the robot can just look at the visual features. This will give the robot information about what class, so what cluster was selected before, which is associated uniquely to a movement vector that basically tells the robot where to put the object to actually pull it optimally. These are some of the results. Actually, the robot acquires about 86% movement accuracy using this method, which is fairly okay. It's not, I mean, it can be improved, but knowing that there's no actual 3D information in the images is quite good to start with. And the method is, the nice thing about the method is they're completely, let's say, self-supervised. I mean, the robot just tries, collects the data, and does all what is needed to obtain the best possible performance while it's moving. So the video finally shows this in action. It shows the initial training procedure, so the robot looking at the tool, extracting the visual features out of the tool, as I explained earlier, and then performing movements, different movements with different orientations of the tools, just to try to understand how well each possible action will perform. From the video, it can be seen that certain actions are completely a failure, others work a bit better. And of course, this in many cases probabilistically, because the robot is not accurate enough often to pull always exactly in the same way, so there are minor differences that may happen. But this is taken into account because we collect large amount of data, and the machine learning sorts this data into clusters, and then when it's time to use what has been learned, it actually works pretty well. So the video is a bit slow, but I think it shows what's happening, how the data are collected, and also the fact that the tools may have different results depending on how they're used, which is very important. At the end of the day, if I have to show the robot how to use a screwdriver, I will need to show the robot that has to be inserting a screwdriver, I don't know, normally with respect to the screw, and placing the screwdriver accurately, and then pushing in a certain way, and then turning. So it makes, there's a lot of details on the physics of the interaction between the objects that has to be taken into account. And here we show actually the test of the system. So an object is presented, and we can go back into the, let's say, movement data that's being stored in the robot memory, and find the maximum, which is the maximum of the probability of actually pulling the object closer. And that's what is being shown here. It's shown for the different orientation of the tool, also showing that in certain cases it will fail, because simply that particular tool is not good to be used in a certain orientation. And I wanted to add a couple more things. Going to this vision that I do tool use and then I grasp the object is one thing that we never mentioned so far, which is grasping. I go over that very briefly. For grasping, you need to have 3D information. There's no excuse, basically, because a flat object is difficult to grasp, and an object for which you don't understand the 3D structure, there's no a priori information how to place your fingers to grasp it. So what we done was actually use the fact that the robot, the iCub, has 2 cameras to recover a 3D structure using stereo vision of the object. And then that's fairly accurate. And from a single view, we take whatever we have and then we try to figure out how to place the fingers. In this case, we concentrated on something called power grasp, which is placing the palm and closing the fingers. Placing the palm at the best possible location, then closing the fingers. And we developed a grasping pipeline that is shown in the next slide that basically shows that we reconstruct the object in 3D. So we have a point cloud representing the object. We segment the point cloud in surfaces, looking for the normals. So surfaces that are almost flat are labeled as a single surface. So the object will be a collection of surfaces. Then in order to grasp the tool, the object, what we do is to look at the surfaces that have a size that is similar to the palm of the iCub. The rationale is that once you have an area which is more or less flat and has a similar size with the palm, if you go there and then you close your fingers, you're likely to be grasping the object. We added a few more checks, let's say, to make sure the grasping is actually stable. So there are quantities you can measure to verify that what you're doing is not completely insane, that the grasping will actually be roughly stable. We don't have at the moment evaluation of the interaction forces, or better, we don't have the software for doing that. The skin of the robot will be probably enough, but we're not there yet. So we can only look at the geometry using vision. We cannot really understand whether an object is leaping from the robot hand. That's something for the future. And the next video shows grasping, in fact. And what happens here is there's a number of objects that are presented to the robot, and the robot grasps all of them more or less successfully. I mean, depending on the object, we obtain good performance. For certain objects, it's almost 100% grasping accuracy. For other objects, it's more difficult, like bottles are kind of difficult to the robot because they observed from a single point of view. The robot doesn't have a general understanding of the shape of the object, so it tends to grasp the bottles from top, which is reasonable, but it's not the most stable configuration. And then boxes and all common objects are actually shown here. And this already entails, let's say, the possibility of combining object recognition with a memory of the object shape from previous grasps, so that the robot can go faster at identifying an object and grasping it once it happens to observe the object more and more during the day, for instance. Okay, so that's it. This can be combined, in fact, in a video that shows the robot using all these different abilities for solving a task that is fairly interesting. So it's the task, we call it clean the table. So there's a table full of objects, and what we like to do is to collect all of them and put them into a basket. So it's very simple, but it basically puts together object recognition, tool use, because the object to be reached can be out of reach, in fact, grasping, and all movement control that we mentioned earlier. Even force control is needed, because if you're collecting an object from a table, then it's good not to break the table. It's good not to break the robot because you're exerting too much force. So compliant control is very important when you're doing interaction with the environment, and this is a case where the robot is interacting with the environment. So the video shows at a bit slowly, but okay, the robot grasping two different objects, and then understanding that one of the objects is too far away, and therefore looking for a tool. It has a rack with different tools, so it grabs one, and brings the object closer and grasps it and puts it into the basket. And then there's a fourth object that is too far away. And what we show here is that the robot can actually do something else, can exploit the fact there may be a person around, so can use face recognition, identify the presence of a person, and speak and ask for help. That's sort of showing the type of interaction we like to achieve and the type of skills that can be placed into a robot. And this is all technology that is more or less available now. It's definitely not 100% robust, which sort of in the long term may prevent a proper application, but it's something that we believe with a focused certain amount of research in a critical mass for these things can be brought to, like 100% accuracy. That's not unthinkable. As I said, for object recognition, but also for tool use, these are experiments we couldn't possibly imagine a few years ago, but these technologies, these AI-related technologies certainly work very well. And there's considerable investment worldwide around these technologies, and the idea is that we can actually very, very well get to the point where a robot like this may be doable.